At the beginning of the semester, we had a discussion. Well, not quite at the beginning, but when we started Newton's laws, we went through the three laws. One of the laws, in fact, the first law is the law of inertia. And we had a kind of broke down a class discussion to reconsider our perspective of what mass is. Remember that I reviewed a couple of definitions of mass that you generally get from other disciplines like biology and science. For example, the chemistry class or biology and chemistry. Chemistry class, the professor might say that mass is something that has volume and takes up space, or maybe that's biology. In chemistry, um, the definition is generally something like the amount of matter contained in a substance. And I mentioned that those things don't help us, that the first law of motion involves an understanding, a slightly deeper understanding, or a physical understanding of what mass is and how mass contributes or to motion or the lack thereof. And we needed to redefine mass in the context of the first law. And so we ultimately found that mass is not only associated with inertia, but in many ways you can think of it as the quantity that defines inertia. Inertia is resistance to change in motion. And what we find is that mass determines the relative resistance to change in motion as compared from one object to another, so that we can describe mass as a quantitative and qualitative measure of inertia. So mass is a measure of resistance to change in motion. This is the definition that we came up with for inertia and for mass and inertia. So inertia It's important to note that in this definition of inertia, It is not resistance to motion, but rather resistance to change in motion. Specifically, the first law states that if an object is at rest, it will stay at rest. Or if it's in motion, it will stay in motion. Nothing with inertia is not, nothing about mass or inertia will resist the motion itself. But if you try to change that motion, and motion basically means velocity, if you try to change it, even either magnitude or direction, either one of those things is a change, and therefore, the more mass you have, the more difficult it will be to make that change. So, if that's inertia, then mass, as we just said, is a measure of this quantity, a measure of inertia. Measure of inertia or a measure of resistance to change in motion. Okay? Well, we have an analogous quantity in rotation. It's related to inertia, but it is it's a separate quantity, and it's called moment of inertia. Moment of inertia. So this is how we define it with regard to linear motion. I guess I could say. We could say with regard to rotational motion, that moment of inertia is the rotational analog to inertia. And I want to be very specific and point your attention to the specificity. That moment of inertia and inertia are not the same thing. So a lot of times people like to use the word inertia as a short, you know, as a shorthand notation to moment of inertia. But it's confusing because, and I don't want it to be confusing. So whenever you're talking about just mass or linear motion, I would like you to refer to the inertia as just inertia. And when you're talking about rotational motion, make the effort to say moment of inertia. Now, for those of you who have calculus 3, you should be already talking about this, I believe. And in most calculus books, they actually show you how to do what we're about to do, but they do it because technically, usually, moment of inertia involves second and double and triple integrals inherently. Um, and so you usually don't encounter this physics until calculus 3. Now, I think I have already started the process of showing you how to integrate with using the quantity mass density to convert double and triple integrals to an integral over a single variable. So we will continue that here. But if you encounter it in math books, a lot of math books, they might introduce it as a moment of inertia, but then throughout the chapter, they also begin to refer to it as just moment. Well, which is not so bad because that's still one word, but it's not inertia, right? So you're not confusing it with moment, inertia between rotational. But there is something else that we will talk about next chapter called the moment arm when we're talking about torque. And so it can be confusing as well if you just refer to moment of inertia as moment, because oftentimes people just refer to moment arm as moment. So just to avoid any confusion, it's kind of a pet peeve of mine. I'm spending a little time on it. Inertia is inertia. Moment of inertia is moment of inertia. And when you're speaking about torque and the moment arm associated with that, just say moment arm as opposed to trying to abbreviate them because it can confuse the communication. And also I want to point out to you that these are three different things. Um, okay, so moment of inertia is the rotational analog to inertia. So if we give it its own separate definition, we can say that moment of inertia is resistance to change in rotational motion. All right. And I guess I could illustrate this before I write down the equation. It's an empirical relationship, the formula, so there's no real derivation to it. You just observe things rotating about an axis, different shapes and things, and you come up with this formula. But there is one demonstration I can probably do that will help to guide your attention, your understanding, that is, of what inertia is, and also understand this equation that I write down. So let's take a trip back to childhood when we are um, playing in the playground. And at least, well, I don't even know if they have these things anymore, but they used to have like swings and seesaws and stuff and monkey bars, all different types of shapes of monkey bars on the playground when I was in elementary school. Now I think many of those they've taken off for safety reasons. People start suing. But anyway, we had those things. And one of the things we also had was just a straight up balance beam. It was like either a piece of wood. I think we actually had just a pipe tubing, which was probably about a 2.5, 3 feet off the ground. Sometimes they're closer to the ground, like 6 inches or so. It was just a bar, probably about 8 feet long, and maybe a circumference about, I don't know, diameter or radius of 3 or 4 inches, maybe something like that. And you just balance and you walk across. You do that. And if you remember trying to do that, or even just trying to balance on, you know, walk on the lines of on the sidewalk or something like that. If you remember when you used to try to do that, what you found is that whenever you're walking across the beam, it's pretty narrow and you kind of lose your balance. You like want to tip over. Now, if I could create a representation of that, let's say that this is the line upon which you were trying to walk in, and this cylindrical marker represents your torso. When you fall, now clearly we don't stay rigid when we fall. We try to jump off or use our legs, or whatever. So we might not think about falling as a rotation because of the manner in which it practically happens when you're a kid. Unless, of course, you just fall asleep standing straight up. Generally, people kind of move their bodies and contort their torsos as they fall. But if you were some sort of acrobat, like Cirque du Soleil or whatever, and your feet were attached to the bar in some way that wouldn't break your ankles, maybe it was some sort of pivotal attachment with your feet. If you kept your body rigid, essentially you would rotate over the bar like that. It would be rotation. So whenever you're here and you're losing your balance, essentially that's the beginning of a rotation that if you kept your body stiff, you would just rotate around the around the axis of the bar upon which you're walking. Now, in order to prevent the start of that fall, instinctively as a 3, 4, 5-year-old kid, what you realize is that somehow, you probably didn't think about it, didn't know, but somehow, just by, well, you tell me, anyone, Arnulfo, if you remember this kind of scenario, what's the first instinctive thing that you would do when you're trying to balance a walk across a thin line as a kid and you're about to fall over? Physically, you adjust your body in some way. Do you know what I'm referring to? What is it that you do? Are you there, Arnulfo? What about you, Armand? So this takes up time. So
I,
whenever
I
so if
think
I
the
could just get it, hands up. Go
I
ahead.
think the first thing I do whenever I'm like on like a tightrope or a string as a kid, I'm like falling down is I well maybe a bit too specific, but I try and like shift myself in a way whenever I'm like about to fall to try and like regain my positioning. Like I try and shift my center of balance.
Wow.
Probably like yeah, I would like try and like move my arms to the right or try and like depends on which way I'm falling, but like try and like just I'm trying to word it, but it's not coming to my mind. But
Well, you got pretty good wording. Go ahead.
if I'm like falling to the left, I try and like shift my hip or like my body to the right, or like try and put my arm like to try and like get my body back in balance.
That's true. That's true. Yeah, you might try to swivel your hips like that or whatever, but there's something that you also do with your arms, both your arms simultaneously, usually.
Oh, like you put them
Um,
out, like you put them out, kind of.
yeah, yeah,
Sorry
good.
for cutting you off.
Oh no, that's all right. You're fine. I cut you off probably. Yeah, yeah. So I would agree. That's exactly what I was referring to. Like you start to kind of swarm around, like it just happens instinctively. Maybe if you're falling that way, right, your hip kind of does something like that. But you also see how my arms kind of come out, right? And generally, once you do that a couple times, in order to even avoid that, you might actually just start with your arms up as you walk across, right? You're balancing like that. It's just an instinctive thing that you learn without thinking about it. And then, if you happen to go to a circus like Barnum and Bailey used to tour, at least still when I was a kid, I think they still do, or the newer ones like Cirque du Soleil, then what you see is the tightrope walkers. They actually have something that mimics that. It's a bar. It's usually about 20 feet, pretty long. And although you've probably never picked one up, they're actually pretty massive. Um, and I've actually held one before and walked, and it's amazing. It's almost like when you hold those things, it's like you're floating across the water. Like you almost can't fall over. You have to hold it rigidly, of course, but if you hold it so that it's rigid with your body, it's just like you can just walk across. Like you don't tend to have that feeling of losing balance at all. It feels like you're just walking on, a regular, a flat surface. It's quite uncanny. And so what actually is happening in that situation is that, and you said it actually correctly, you are, well, if if your center of mass is somewhat off, then doing that will shift it back. But the point is, when you're balanced on the line, you're already your center of balance, center of mass is already balanced. But because of slight inconsistencies of walking and things, it can throw that off. So doing that is kind of a way indirectly of indirectly affecting the quantity that I'm about to talk about, but it does directly get your balance back for the moment. But holding it out like that before you even unbalance, it actually directly addresses this other quantity that I'm talking about. And the other quantity is moment of inertia, because it increases your moment of inertia by shifting your essentially hands outward. And ultimately, the physics behind that is that the farther away that mass is distributed from the axis of rotation, the larger your moment of inertia. So, for example, if you had two balls of the same mass, one is a solid ball, which means, and the other is a hollow ball. Now, if they're the same mass, that means that the solid ball has to be much less dense than the uh, the hollow ball if they have the same mass, because that means that the mass of the hollow ball is just distributed over a thinner portion of the diameter of the overall ball. Um, but if you would then have that same mass, same shape, radius, and curvature, and diameter, everything, but one is hollow and one is solid, which one will get to the ground first if you start on a ramp and roll them down from rest? Well, moment of inertia is resistance to change in rotational inertia. And if I qualitative just said by placing your right, it's like it's your body, right? It's the same mass. You're not changing your mass, but if you put your arms out, then you have basically the axis of rotation goes through. Well, you got two really. There's an axis of rotation that you're walking on, the balance beam that you're walking on. But technically speaking, we can kind of think of our torso can move when our legs don't. So you can think of your torso as having an axis parallel to the axis that you're walking on that goes right through your heart. And that's the axis that your arms can kind of pivot around. But ultimately, those two parallel axes, if your body is stiff, you can kind of think of them as the same. And so if you're keeping your body stiff, then if this is the axis and my arms are in, as I put them out, there's more mass of my body distributed farther away from the axis of rotation. So in general, anytime that happens for the same amount of mass, the moment of inertia will increase. So for the solid ball, if I take some of the mass that's in the middle and reform the ball so that it's, the mass is distributed near the outer portion of the ball. So here we have a solid ball, right, of mass M and radius R. And then we have the same ball, same size, mass M, and same radius R. But we reform the ball so that all the mass is just in a thin portion thickness here on the side. Then the moment of inertia. And the symbol that I'm going to use for moment is capital I. So moment of inertia, I would say the symbol is I. We'll talk about the properties in a minute, but it's a scalar property. Scalar quantity is not a vector. And it's related to mass. So in the same way that mass, which is inertia, is a scalar quantity, moment of inertia is also a scalar. So if this is mass 1, particle 1, we'll just say mass 1, and this is mass 2. We've already made a point that mass 1 equals mass 2. This equals the mass m. And what we can say is that the moment of inertia for ball 1, I1, is actually less than I2. And you know that simply by looking at them at this problem. In fact, this might be like on some sort of standardized test, like a GRE or something. They might give you some problem like this: two balls, same, radius, same mass, which one has more inertia, and understanding that the difference in the construction is that one is hollow and one is solid. That could be a qualitative. In fact, even Wally might give some sort of problem like that. So qualitatively, then you can look at it and tell that all the mass is distributed away from the axis of rotation, and axis of rotation goes to the center. So therefore, you can say that M2 has a higher moment of inertia. Moment of inertia, excuse me, is resistance to change in motion. So if both balls started on a ramp, the one with more resistance to change in motion, because initially, if there's started at velocity 0, there is no motion. So, and everywhere through, as it increases its velocity, the moment of inertia is always, affecting it because the velocity is increasing. It's trying to change, or changing. So, the one that is hollow will take a longer distance to fall down the plane, because of this quantity. Yeah. Well, with that said, we can just write down, at least for a discrete system of particles, what the moment is. By definition, and the moment of inertia is defined as the mass of an object times. Now, here's where you got to be a little bit careful. Times r squared. Now, in this case, r does not represent a radius. In fact, let me change this out. So I know we normally use r for radius, but I can use anything. I'll just call it a here. In this case, r is not the radius. It is the position of a portion of the particle from the center of mass. Yeah. You know what? Let me say this differently. Let's say this. Let's say that we have a system of particles. Let's go with that. System of point particles. Well, you know what? Let's start with the point particle first. Let's start with the point particle. Yeah. Let's say that, yeah, let's do that. So just one particle, and it's a point particle. And let's say that that particle is, I can put it on the end of a string and twirl it around. I've done this before. Now let's assume that this meter stick or this ruler is massless. And at the end of the stick, I take a little point particle and tag it on. So if I flip it around like that, then the point particle will oscillate just like a particle at the end of a string. Now let's say that we're looking, well, let's say that it's going to oscillate in the two-dimensional plane of the board, and I can describe an axis, a simple axis problem to have this thing rotating. Right? This is X, this is Y, and I have a little string, and my particle is on the end, say here, a particle that's mass, M, and to represent the string or the odd thing that's, it's pivoted, the axis of rotation is going to be the origin. And so I can represent the string as a position vector, r, to that particle. So that's what r will represent. In this case, it'll just represent a position of that mass. Now, in subsequent considerations, we're going to have to expand our understanding of what r is. But for a simple point particle that's rotating about the x-axis in a circular fashion, like so, then r just represents the position of that particle relative to the axis of rotation. So we can establish that r is then the position of the mass, or for continuous particles. So yeah, so R is the position of a particle from the axis of rotation. Actually, it's from the origin, but generally we place the origin at the axis of rotation. I'll say origin / axis of rotation for a rotating body or particle. So for a simple one-dimensional point particle like this, the position vector and the r in the moment of inertia equation are basically the same thing. I guess it always kind of is, but particle. But it actually is a little bit more than that as we get more complex particles, and I'll show you what I mean in a minute. And it basically, for a system of particles, and I think I had you, like we talked about, like if I had a balloon and I blew it up and I put black dots on the balloon, and those would represent system of particles, and it's like a rigid body because they don't change their distance relative to one another. So in that case, if I had a bunch of dots on the balloon and I twirled it, each of those particles, and let's say that the balloon is massless, so the only thing that has mass is the particles, at their various distribution points. Well, those particles would each contribute to the moment of inertia of the overall system. And moment of inertia abides by superposition, so that the total superposition, the total moment of inertia of the system of particles would just be the sum of the individual moment of inertia. Sorry, let's say that the total moment of inertia, yeah, is just the sum of the individual moments, moment of inertia, moments of inertia for each particle. So by definition, then I is equal to mr squared. And I think I defined this. This actually came out of the definition of the kinetic energy on last Monday. So we defined it, and I told you I'd come back and talk about it. So we already have the definition. That's for one particle, a particle like this. But as I just said, for a system of particles, the moment of inertia abides by superposition. So if I had various particles, um, rotating around, each of those contributes to the moment. And maybe a good example that just popped into my mind is the galaxy, is like the Milky Way, right? That's goodness knows how many particles are in our galaxy spinning around the black hole at the center of the galaxy. And all of those solar systems and stars, I'm sorry, yeah, that's a galaxy. Yeah, so galaxy is made up of billions of star systems, and those star systems have their own planetary systems associated with them. So yeah, yeah. So I don't know, maybe like the Milky Way, maybe something like that, right? A spiral type galaxy, kind of looks something like that. And these things are very, you know what? Maybe that's a little bit too much because it doesn't really show so far away. It doesn't show the individual particles. All I'm trying to say is that you have one particle like that. If you had some sort of system of particles, and maybe the center of mass could be arbitrary because the particles don't necessarily have to be the same mass. even if they were the same mass, then maybe, I don't know, maybe the center mass might be shifted more toward the side with more particles. But just let's say that that's the axis right there, right? And we could represent it as a three-dimensional axis. That would be two-dimensional. Three-dimensional might give us a better perspective. All right, so if we had a three-dimensional axis like so, and we have these particles that have various perspectives about our various positions about our axis, about our origin, our coordinate system. And they're all rigid, maintaining the same relative distance to one another. If I then spin the axis, the y-axis, like so, then all these particles will spin around. You can think of it like that. And so they're all kind of mapping out circles in the horizontal plane. So for example, this guy might do something, like this in its plane. This guy then goes around. It's got to be centered on that thing. So maybe something like this. This guy is going to have another, circular orbit. It goes around like this. And all of them, just various, positions as they're moving around. So, in this case, the total moment of inertia is going to be, the total moment of inertia is going to be, at the formula, I total is going to be equal to the sum of all the individual moments of inertia. Like I said, so you have like an m sub I, r sub I squared, where each of these is like 1, 2, 3, 4, 5, 6. And in this case, for this system, our counter would go from 1 up to 5. Okay. Now, there's something, as I said, as we get more complex systems, we have to kind of uh, expound on what our position vector actually is. So we'll do an example here in a moment that will prove this. But r is really the perpendicular distance from the axis of rotation. In other words, let's say that, so in this picture, the idea is that we were rotating about the z-axis. That's the implication. I didn't specifically say it, but I did. The z-axis is coming out, and we're rotating around like this. So this actually is the perpendicular distance from that axis. But it's important, you have to understand the orientation of the rotation in order to truly define R. I guess as you're first learning to understand what R is. So I didn't say that there because it might have looked a little confusing, but I need to say it over here because there's no way I can show the perpendicular distance because it's perpendicular to the axis coming out. So here we have to kind of change that a little bit, or at least add, qualify it, in that it is the distance that in these problems, since the y-axis is pivoting, r represents the perpendicular distance of each of these masses from the y-axis. So like this distance, well, this situation, this would be R1 here, or R4, I guess, here. And then R6 is here. And R3, it looks like it's in the XY plane. It would probably be right along the axis there. So if I were looking down the z-axis, that's what I would see, right? In fact, in this picture, my mass actually was on the x-axis, so it would be really at this point. But that gives a comparison of r in this picture as compared to r over here. So this is like, yeah, so what we can say here is r is the perpendicular distance that an individual mass or of a system or a differential mass element, as we'll see in the next example, is away from the axis of rotation. So r sub I represents the perpendicular distance of the mass element, the mass particle, or differential mass element from the axis of rotation. Okay. Mm-hmm. Yeah. Okay. Now, for a continuous mass distribution, let's take another look. Well, this is a good example here. This would be continuous mass distributions, meaning that they're not separate particles, but you could break up the overall particle into differential mass elements. So like, I could use, like if I wanted to figure out the total mass of this thing, basically the total mass is the differential of, the differential masses. That is, if I pick out a little block, differential block of mass m, and if I add up all the blocks, then I'm going to get the total mass. So this is like a differential, you know what a differential mass is. And so by definition, then, calculus, if I were to integrate, if I were just to create an integral problem, like the total mass then would be equal to the integral of all the differential masses. You're just adding them up, right? Because remember, a sum, this is really just a sum of all the m sub i's as I, but in the limit as delta m, actually it should be delta m, as delta m goes to 0. So as you get a smaller and smaller delta m, you get a better approximation. So in the limit that delta m goes to 0, the summation sign becomes an integral. Just trying to remind you of what an integral is. You're just adding up everything. So if this thing is spinning around some axis, this continuous mass distribution, it's as if all of these differential masses is basically the same picture, but just differential masses that are so small and that fill up everything so that it's hard to see the individual masses. But still, the differential masses are separate elements that have their own moment of inertia and that they twirl around. And as if you want to get the entire moment of inertia, you just add everything up. But we still can maybe establish some sort of axis like this, right? And then we spin the thing around that axis. Right? And again, even if we had and this is an important thing to say. Oh, and yeah, like over here, I could map out, maybe I do a different geometry and I map out like a differential mass there. I know it's two-dimensional, three-dimensional still, but maybe I make this thin though, and I just call that a cross-sectional area. At any rate, there's several ways, depending on the problem, I could do that. But what I want to emphasize to you from this point of view is that if I call this the axis that I'm pivoting around, let's say it's a vertical axis, it's important not to confuse the R in the moment of inertia equation with a position vector. In this problem, it is both. That's what's a little bit deceiving. So a position vector is, if this is my origin here, a position vector and you guys go ahead and put in the third axis as well. Just get used to seeing it from that point of view. I guess it goes through. So a position vector would actually point from the origin to the point in question. But again, this R in the moment of inertia equation, it doesn't have a name. That's why I'm not referring to anything. But it is not from the origin. It is the perpendicular distance from the axis of rotation, not from the origin by definition. So that's actually this distance right here. So I'm gonna just call this, I don't know, maybe A. I don't know what I would call A. That's what I was calling the radius A. But R in my equation here is actually this distance. So that is R, because this is the axis of rotation, and that R vector makes a perpendicular angle with the axis of rotation. And so you can see how for all these different masses, it's really just the perpendicular distance that matters. And again, going back to the original qualitative description I made about how to increase or decrease moment of inertia, it's really about making this mass farther away from that axis. So the farther away it's distributed, the higher the moment of inertia. So again, qualitatively, if I had something like a cylinder compared to, well, that might be a little bit difficult because it's, I have to specify the radius, but I guess the minimum radius of the thing, yeah, I don't know. That's a little bit difficult. But yeah, so I guess I would just leave it at that. Oh, and then for continuous mass distribution, we could write one more version of the equation. This symbol, as I said, becomes an integral, and the mass becomes a differential element. So this is for one particle here. One particle. This is a system of discrete particles like this. A system of discrete rigid particles. Discrete. No, it's not Descartes, it's discrete. Discrete is a proper name. So discrete particles. And a continuous mass distribution, which is represented by the volume of mass here. continuous mass distribution. The moment of inertia would look like this. Would be integral, still representing the summation sign. And then r squared is still there. And dm represents the differential mass associated with the thing. So this is the basic formula for that guy. So that's the introduction to moment of inertia. I'm going to do a couple examples. I'm going to start with something that looks like this. Well, we're going to exploit geometry so that it's easier to kind of work through it. And then we'll talk about that solution, and then I'll let you work on it as a class, and then we'll go to continuous mass distribution. And yeah. So our break is in. I am going to go ahead and break at 2:30, even though we started late. So that's about 3 minutes in. So any questions then? Any questions about? I'm going to set up a working break for you here, so I might go a little bit over. But any questions about moment of inertia and what we've talked, what the definition and what it is? Okay, so I'll read the properties after. So yeah, so let's say that we have a situation here where we have a box. Let's assume that we have a box that has 4 masses, actually 8 masses, in the shape of a rectangular type figure. So let's do it like this. Let's put these together. Actually, make the axis red. Pull that back. This. These masses are bound together here, 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 here. And then we're going to do the same thing in the back. So say we come up here and do something like that. Right over. Here. Okay. So this is a rigid body where these masses have fixed positions relative to one another in the shape of like a rectangular type figure. That's not necessarily drawn to scale. I know it looks like a box, but I was saying box, but it doesn't look like I have all the sides the same here. So these two sides are the same. This is side A, and this is side B. But I wanted to distinguish that the vertical distance, that's I'll call that side B. They're not quite the same length. All right. So B is this distance. A is this distance here. Give it a three-dimensional representation. So here and here. Now, what I'm going to do is have two axes. One is going to go through the center of mass. Now, if we can assume that all the mass is the same, so then the geometric center of this box is also going to be the center of mass. Make that simplification. So M1 equals M2, so on, so through to M8. So we can just call the mass M. And we'll make that equation, I have that equation 1, 2, 3, so 4. And yeah, and so we have two axes, one through the center of mass. So that's going to be this guy here. Okay. And yeah, we can just call that, what do we call that? It's axis, but I know it's not the moment, but I'm just going to call it I. So this is going to, what we're going to do is calculate the moment about the axis of rotation, AOR. And then I'm going to shift that axis over to this corner or make it a different axis. And that'll be we'll call it the parallel axis. So I parallel. What I want you to do is figure out these two quantities. And we'll twirl it around. So they'll go around, like, doesn't matter what orientation, but say we twirl it around like this. So that the whole rigid body is twirling. Well, it's going to be harder to twirl it around one axis than the other because the moment of inertias are different. So what I want you to do is to first, you don't have to tell me, but guess which one you think is going to have the higher moment of inertia based on the qualitative descriptions that we've made. And then prove one way or the other by actually using, and it would be this formula here, to calculate the moment of inertia for the central axis or the axis through the center of mass, and then compare that to the moment of inertia of the parallel axis. Okay. So in this problem, calculate the moment of inertia about each axis. I AOR versus I parallel or parallel axis. All right. So let's go ahead and take a break. Let's make it a working break. And again, to get you started on this guy, like I'll do the central, maybe do the central axis first. It's easier. So, but then expand this formula here. It's just going to be equal to M1, R1 squared. And let's label them. So let's make this one, how do I have it labeled here? So, so we can call the same numbers. So I think I labeled them like this. And let's label them the same so that when we calculate the moments of each individual one's particle, we know what we're talking about. We can compare them. So 1, 2, 3, 4, 5, 6, 7, and particle 8. Okay. And so here we have to calculate the moments, right? So then plus M2 R2 squared so on and so forth to M8 R8 squared. And again, R is the perpendicular distance from the axis of rotation. So basically, for all of these, they're going to all have the same moment. They're the same mass, and that R value would be half the diagonal. It gets a little complicated when you shift over to the parallel axis, but that gets you started. So let's go ahead and do that. Go ahead and work on that. I'm going to give you so what time is it now? 2:35 or 2:36. So let's go. Usually we take 15 or 20. Let's go a little bit beyond that and let you work on that. So maybe go to, 25 minutes to 30 minutes. So between 105 or 3:05. We'll come back around then. All right.
Professor, real quick, what was the question again? I'm sorry. That we need to go ahead and work on.
You need to calculate the moment of inertia of this block that I drew here. And calculate two. One for the axis that goes to the center of mass, and the other for this axis over here. So
Professor, can you turn your iPhone camera towards the problem because it's
ooh, okay.
Yeah, that was way better. Thank you.
Sorry about that. Sorry about that. You got the other cameras as well. Where you see all three cameras?
Yeah, we see all three, but the iPhone one is honestly the best one.
It's the best one. Cool. All right. Yeah. Sorry about that. Awesome. Yeah. So like in the one case, the first case, the axis is through the center. So the rotation would look something like this, right? Like if I took it and now basically, just think about the fact that only the blocks have only the edges, the corners have mass on them, and there's nothing else. It's just hollow, and somehow there's these things are not they're just to guide your eye, but there's nothing really there. But these masses are fixed in space relative to one another, so it makes the shape of a box. And if I were to spin it, it would look something like that, right? So they're just all spinning around on one another. So what is the moment of inertia for that axis? Now, when I shift the axis over to a different axis but parallel, it's kind of like if I had let's just do this, something like a rod, so now my ruler is the parallel axis. So that rotation would look something like this, right? The whole thing would be spinning around the edge like that. That's a very different type of rotation. So what I'm asking you to do is to qualitatively just decide, make a determination of which moment of inertia you think will be greater and why, based on our earlier discussion. But then use the definition of moment of inertia and this formula to calculate the two different moments and then compare them to see if you actually get something consistent with what your intuition led you to believe. So does everybody understand?
Sounds good.
All right, we'll go ahead and work on that. Let's go ahead and knock this out. Just computation. These two moments. Now, yeah, so we start from equation 5. Now, there's symmetry here, so we can just exploit it. As I was saying, if you look at a top-down view, basically the r distance for each of these particles is half of a diagonal of the top face here, or the bottom face. So just to emphasize that, I will draw a top-down view of the system. Okay. So that actually is a square. What we would see are these four particles the top. So I guess that would be particles 5, 6, 7, and 8. Connected as it were. So this is a square. This is sides A and A. And the axis, of course, is right here in the center. So as you can see, each of these particles will be, that's going to be the distance r, namely half a diagonal per second. And be the same for each object. So let's just go ahead and calculate that. We can use the Pythagorean theorem, right? Because we know each side of that right triangle is going to be 1/2 A. Right? If we were to kind of map out a triangle like this, then we have something that is the hypotenuse of the figure is r. R A, actually 1/2 A is 1/2 A, or A over 2, and A over 2. So by the Pythagorean theorem, r squared equals A over 2 quantity squared plus A over 2 squared, and all of that to the square root. That gives me A, basically 2 times A squared over 4, 1/2. And so ultimately, a value for R is going to be is that going to be it'll be A over the square root of 2. Right? But actually what I need is R squared. So yeah, I can just say that R squared, because that's going to be what goes to the formula. It's just A over A squared over 2. All right, so and all the masses from equation 4 here, as we said earlier, all the masses are the same. So to calculate my moment, masses here are all the same. So I could just say that my moment is going to be equal to 10. So this is I guess I said AOR, axis of rotation. Both of them are axis of rotation. I should have subscripted this CM for center of mass. So this is through the center of mass, and this is parallel axis IP. So I through the center of mass is going to be equal to Well, first of all of the terms are going to be the same because of the symmetry. So then 8 times m times the r value for each one, which is a squared over 2. And so 8 goes into, or 2 goes into 8 4 times. So my final moment of inertia for the center of mass axis should be equal to 4 ma squared. How many people got that?
Professor, I have a question.
Yes.
Why did you go back to r squared, um, the original form, r squared versus the reduced form of r at number 8?
Great question. Because the formula in the general formula for inertia, we need r squared, not r.
Oh, okay, I see that now.
Yeah. And by the way, it's really interesting. The thing we discussed last week, or Monday, I guess it was or whenever it was. Maybe that was last week. We did center of mass, and center of mass is it's almost similar to this kind of, center of mass is defined as RCM, but it's a vector, is equal to 1 over the total mass times the integral or summation of r dm, right, where r is a vector. So the integral portion is kind of the same. In fact, you could take the RCM over here. You have m times RCM equals the summations. But basically, since r is a vector inherently, r dot r is going to just be an r squared. It's going to be a scalar quantity. Now, to be clear, that r is different than this r, because this is actually the position vector. This is not. This is the perpendicular distance. In fact, maybe just to emphasize that on all those, you could maybe do something like that. It implies, I don't know. That's a slightly different meaning than position. But the point is, it is squared, and so that's why I don't need the magnitude. I need the square of the magnitude. So that's why I went back. Great question. Any other questions? Did anyone get that? Did you? Who asked that question? I didn't look at the back at the.
Oh, that was me.
It was Joe. Were you able to get a solution for this? Did you get this, or any solution at all?
I got mixed up on the when I reduced it. I forgot that we were supposed to do r squared. So that's where I messed up. But I see it now. That's why I needed to clarify with that question on why you used the non-reduced form.
Yeah.
So is this is the inertial center mass is equals 4 ma squared? Is this like a general formula for something like this question?
What do you mean a general formula? Like this formula here?
Like yeah, like for example,
Remember. Go ahead.
like for example, we get a problem where we're given a similar scenario of like a cube, would this help us out with something like this, or maybe it's just breaking it down to the top view and then from there getting the r and using Pythagorean theorem, correct?
I think the answer to your question, if I understand it correctly, is this is the general. These three equations that I wrote, the summation form, those are the general equations. And that's where I would recommend always starting from there.
Oh, okay.
Right. So no, this is not applicable in general to anything else but this problem. But where did we get it from? We started here and we went through the process of breaking it down, like you said. So that's what I would recommend doing every time. In fact, you got another chance. You got it over here. So now that you got that straight, I want you to see if you could go ahead and give you another 2 or 3 minutes, a class. Go ahead and shift that axis over, and from scratch, start with this version, and then calculate the new moment of inertia using the axis that goes through positions 3 and 7, and see how you fare. All right. And by the way, which moment should be larger, the ICM or IP, and why? I mean, what was your guess? Anybody? Joe, did you guess?
Would it be IP?
And why? Why is IP larger?
Would it be relative to the mass?
Yes, and so I need a complete statement. What relative to the mass? What about the mass?
That's where as much as my guess goes.
Okay, all right, fair enough. So go ahead and calculate and see if your guess is if you validate that. And while you're working the problem, maybe you'll be able to kind of articulate what it is the mass has to do with, why, what is the relationship of the mass to the moment of inertia, and how does that relationship change as you go from the center of mass axis to the parallel axis. All right. Let's go ahead and work on that again. Right. Well, from this picture, let's come back to this guy here. So my new axis, my parallel axis, is going to go through 0.7 here. IP is through there. Now, that means that R for mass 3 and mass 7 are 0 because they're position vectors. Well, the I is 0 for those because their position, well, it's not position vector, but their R value is 0. So R7 equals R3, or R squared, is equals 0. So that leaves only 6 other terms. Terms 8, 4 and 8, and 2 and 6 are going to have the same value, and their distance will be, their R distance is A from the axis of rotation. So for those 3 or 4, so that's going to be 4 particles that have that moment. So IP then is going to be equal to 4 times each of the masses, which is just M, times the distance that they are from the axis, which is A squared. Okay. Now, the last 2 particles are particles 5 and 1. And their distance from the axis of rotation is the full diagonal. These 2, and like in this case, that would be here. And so that distance would be the full diagonal cross. And again, if you kind of think of a right triangle, then we can kind of reform this, that R value is now going to be equal to, well, the sides are A and A now. So that would be A squared plus A squared, which is 2A squared. And that's what we need. We need the square of that. So R squared is going to be equal to 2 times A squared. So we have 2 particles. So then that contribution to the moment would be, right down here in a second. So I have 2 particles, so that's 2. The mass is M, and the value R for this case is going to be So it's a squared, the square root of a. R squared is equal to a squared plus a squared. So that's going to be just 2a squared. So when you add all that up, you got 4a squared plus basically 4a squared. So in that case, the moment of inertia should be 8m a squared. And so it looks like Joel was correct. His intuition was correct. That when you, just by shifting the axis of rotation over to the side, it increases the moment of inertia, it doubles it. Doubles the moment of inertia. So it's going to be twice as hard to rotate the system around axis through the points 3 and 7, even though technically I'm actually taking 2 of the masses out of the game. They're not contributing at all to the moment. Yeah. Yeah. So there you go. Yeah, it's so basically kind of the takeaway. Actually, Joe, I wanted you to think about trying to explain again. So you want to take another stab at, so you basically got it right quantitatively. But if you're trying to just explain it to someone and describe it to someone, have you come up with some better rhetoric or language to do so while you were working through the problem?
So before I attempt to, I had a question actually.
Okay, go for it.
For step number 12, why is 7 and 3 equal to 0 again?
Yeah. So if you look at the side view over here, in our formula, mr squared, r represents the perpendicular distance that each mass element is from the axis of rotation. So in this picture here, the axis of rotation is this guy. It's just a line going straight down the side there, right? So each of the masses have mass value m, obviously, but how far are they from the axis? Well, they're literally, the axis goes through them. So that distance that they are from the axis is just 0.
Oh, okay, that makes sense. Oh, okay.
Yeah.
Oh, okay. I see what you're saying now.
Yeah.
Okay.
And just to follow through, for objects 6, 2, 4, and 8, you can see from this picture that that distance is a. And also this distance here is a. So for all those 4, it's a. And then, of course, for 5 and 1, you got to go all the way across the top of the surface along the diagonal. And so that's what I was calculating from this point of view.
So you're saying as we rotate from the axis of 7 and 3, in order to get the center of mass, we have to go ahead and look at the diagonal from that axis, and diagonal from that axis is from 7 to 5, and then that's when we use the Pythagorean theorem to get the center of mass.
Okay, we're not calculating center of mass. We're calculating moment of inertia. Is that what you meant?
Yeah. Sorry about that.
We're calculating moment of inertia, and in the process of calculating moment of inertia using this formula here, we have to determine a value for R. R in this formula is that, let's call it R perpendicular, because I just want to give it some kind of name to distinguish it. R perpendicular is what I'm doing when I'm using the Pythagorean theorem. R perpendicular is the perpendicular distance that the mass is from its axis of rotation, how far it is from the axis. So that's what I was doing. Over here, like I said, if I draw the diagonal, so this mass, it's across the perpendicular distance, right? If I have the box kind of like that, the edge, this is the axis right here. So if I'm at this space, perpendicular distance means diagonally across from that axis, right? But in the plane. So the axis runs vertically. The axis runs vertically, but the perpendicular distance is this distance over to the mass sitting on that corner on the edge over there. So
Okay.
looking down, say again?
I said okay.
Yeah, so looking down at the top face, this is the picture that I drew to represent that. And so we can see that that diagonal represents the distance for mass 5 and mass 1. So unlike when I was calculating the moment of inertia for the axis that goes through the center of mass, where all of the R values happen to be the same, it breaks the symmetry a little bit by shifting the axis over to the edge. And so different groups of masses have different R perpendicular values that we had to calculate or find in some way. So does that make sense?
Yeah, that makes sense.
Good, good, good. I appreciate your class participation. I'm going to go ahead and answer the question I asked you. So your intuition is good, but the language that I would use, what you were trying to say, I think, is that, or one way to say it, is that the more mass of the system that is farther away from the axis of rotation, the higher the moment of inertia. Right? Because when the axis goes through, there's no mass in this system that is more than half A away from the axis. Right? That's what we were saying right here, or wherever it was. Actually, it's not half A. It's half square. It's A over square root of 2. Actually, well, I'm sorry. That's all. Yeah, right. Yeah, yeah, because it was half the diagonal. That's right. So A over yeah, but whenever we switch the axis, well, now you have, some particles are A away, and that's 4 of them, and then 5 and 1 is whatever we just said. That's what was that distance? I guess. Well, I have to recalculate. I don't remember what off the top of my head what it was, but I guess it would have been the square root. We didn't calculate. I just kept it as A squared. I guess it would have been A 2, the square root of 2 times A distance away. Anyway, we could find them, and we find them, and we just put them into the formula to determine it. But you see that, like, and it's kind of, it's not like a linear relationship. One, because it's squared. The relationship between, I is proportional to R squared, not R. So it doesn't just go up linearly. So you can't really, it's hard to estimate, because in this case, for example, you might think, well, since I'm taking out 2 of the masses, even though I have more mass farther away, maybe the moment of inertia I do have more mass farther away, but it's only, in fact, it's only 6, 6/8 of the masses. It's not 8/8. So in other words, I only have 6 particles. I don't have all the mass. So even though they're farther away, because the total mass contributing to the moment of inertia is less, maybe the moment should decrease. Your intuition might lead you there, but that's more like thinking of the relationship between moment of inertia and R as a linear relationship. If it were linear, that's probably the case, probably would be the case. But you got this square term in there, so the distance is square, right? So even though you only have 6, one is, very far away, and the others are at least half the distance, twice the distance that is of, the length of the thing. So, it just, you can't really determine it so much by numerically, but qualitatively, anytime, just like whenever you're on you're on your balance beam and you put your arms out, your arms are not a great deal of the mass. It's a smaller percentage of the mass, as appendages go, certainly smaller than the mass of other appendages or parts of the body. But simply by sticking your arms out, it drastically increases your momentum your moment of inertia in such a way that it's much noticeably easier to balance. That's again because of the square term here. Like, even though my shoulder portion might be heavier than my hand, or more massive than my hand, it's not that far away from the center of mass of my body, the axis of rotation that you might be considering. Whereas my hand is, a whole meter away. So or maybe more. And so when you square that and multiply by the mass, that quantity, mr squared, of just that small portion of mass, represented by my hand, might actually be larger than the mr squared associated with a larger portion back here on my arm. And you can say that for anything in your body. So yeah. And it ends up being twice as much the moment of inertia, even though you have, I guess, 2/8. So what would that be? 2/8, one, yeah, 2/8. So that's 25%. So even though the mass is decreased by 25% for the second configuration, the moment of inertia goes up by 100% because it's twice as much moment of inertia. Anyway, yeah. I could outline some properties, basically properties some of which I just mentioned, which I'll do here quickly. It's kind of nice to have that. But the general thing is, if you have more mass distributed away from, an object for the same amount of, from the axis of rotation for the same amount of mass, then the moment of inertia is going to increase. But moment of inertia is proportional to r squared. That's important to know, not r. It's also proportional to the mass. It's a scalar quantity. So you don't have to worry about doing any vector analysis. And you can see that here with these equations. Once we figured them out, we just added the numbers up. It doesn't matter where they are, because, it's not a vector quantity. So that's nice, because center of mass is a vector quantity. We did have to get those, get the, and I'm comparing it to center of mass just because mathematically that integral portion, they look kind of similar mathematically, and so you might be tempted to kind of think of them as same, but they're drastically different quantities, even though that's the case. That's why I keep mentioning it. So these are properties. Also note that r is the perpendicular distance from the axis of rotation, as opposed to a position vector. I mean, if it's cylindrical coordinates, that is a position, but in general, we kind of represent this, and I did before, as spherical coordinates, like a three-dimensional space, not just spherical geometry. So in that case, r generally means a position vector, but here we're specifying that it means the perpendicular distance from AOR, which in general is not a formal axis of rotation. I got this, and then I guess I could say superposition applies. So that's what allows us to be able to do this, right? To add them up. The superposition of a scalar quantity is pretty straightforward. Yeah. So that's for discrete particles. It's for discrete particles. However, we could calculate the moment for continuous particles as well, which I'll do one or two of those for you. By the way, the moments of inertia, you might, once I show you a couple of these, you might want to practice. Be helpful. It's what I did, and others to kind of learn it. And one thing you can do is in the chapter, they're going to give you a chart. You might have already found it with moments of inertia for different physical configurations. In fact, in that, you can kind of see this trend that we're talking about. So if we go to the book here, go to chapter 10, and it's just calculating rotational inertia. Here you go, 10.5. So you see the formulas there, different ones for discrete and continuous charge distributions. That's the parallel axis. That's something I'm going to do last. But here you go. Here's the chart. And you can see some examples of what I'm talking about. So here's a hollow ball. So this is a solid sphere. Its moment of inertia is 1/2 mr squared. So assuming that the m is the same value, you go over here with the hollow sphere with the same axis of rotation and the same mass. What would you expect? Well, as we've just pointed out, that moment of inertia should be larger. And is it? In fact, that's, oh my gosh, my eyes, I can't see it. Is that 2/3? Is that
Yes.
2/3 mr squared? Yeah. So yeah, 2/3 is greater than 1/2, right? If you had to break that down to a fraction, you can do that, but it is, yeah. So the moment has increased. It's increased because of that. And where's another good example? I don't know. Yeah, they don't have any really good ones. The cylinder would have been a good one, but they don't show it quite. They don't go from a solid. Well, maybe because this is a solid here. This is a solid. Yeah, that's solid. And then here's a thin one over here. So I know they don't look like they're the same, but let's assume that this length was the same. In fact, that's another thing. Actually, I forgot to point that out. This is illustrating that, well, let's just say, like, assuming those were the same length, because you see length is not anywhere in the formula. So if the mass were the same, I could redistribute that so that it was the same length as that cylinder. So here you would have a solid cylinder, and here you would have a thin cylinder. And if the moment of inertia is 1/2 mr squared, and assuming that the radii are the same, then by distributing all the mass on the edge here, 1 is greater than 1/2. So the moment of inertia would just increase, right? Because I redistributed the mass on the outer edge as opposed to having it all the way through, assuming the same mass. So that is showing that trend. And the other thing, I'll come back and show you on the board, but it also is illustrated here that because they made these different radii, like different lengths, it doesn't matter in the case where the masses and the radius would be the same, because it's not the L, the perpendicular length, doesn't show up in the formula. So it doesn't contribute to moment. That's why I keep saying perpendicular distance. If that weren't the case, then we'd have to actually do a position vector, which would make the integrals much more difficult. But the only thing that matters is how far, the perpendicular distance that the mass is away, not where it lies along the length of the axis. So that's why you can see here that 8 and 4, they have the same formula for a moment of inertia, even though they're different lengths along the vertical, but they're the same distance, perpendicular distance away from the axis. And so that's the thing. Okay, good, 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 good. I just thought of something in my head that might reiterate this. Coming back to something that we know intuitively, the walking on the balance beam. So let's say that I'm on the balance beam and I already understand, I already know that if I hold my arms up, that's going to increase my moment of inertia. So I start out like that. But then I want to experiment with certain things, just playing around intuitively. I might think, well, what if I do something like this? Will that increase my moment of inertia? Right? And how does that compare to this? So I'm walking along, so I might do it a couple of times, and I realize that if you are that sensitive, or maybe you have a really long pole, like that is mechanized, so you can make the arm shoot out or come in or something like that. That would probably be something better to experiment with. So you could do a drastic difference in the length of the pole. But what you would find is that this does make it, like if I'm walking, this makes a difference, right? Because I'm bringing my mass closer to the axis of rotation. So it's decreasing the moment of inertia. But once I have it here, if I do something like this compared to that, or this compared to that, it changes the moment of inertia, not at all. Or a better way to think about that is that if I had a long pole and I did something like this, or this, or this, it wouldn't change my moment of inertia at all as I'm walking along. It would feel the same. But if I had it mechanized and I could take the ends in or out, that would make a difference. So that's what you're seeing there implicit in those formulae, that the L, the length of those two was noticeably different, and they didn't even say anything about it. And it does, because it doesn't show up in the formula, and this is why. So these are all the properties associated with the moment of inertia. Even though it's a scalar quantity, it's a little bit more subtle, I think, than center. I mean, center of mass is pretty straightforward. It's like you just the definition of the thing tells you what you're talking about, and we all know about symmetry and that sort of thing, and have had some experience with that, even starting from our playing as a youth, when we're younger. Moment of inertia you never heard of before, sure, and it's obviously more subtle. Yeah, yeah. So, any other questions before we move on to continuous mass distribution? Oh. One moment. Okay. Guess I could calculate some of those. Why don't I do that? I'm going to go with, I'll do the ring, and then I'll do a disc. Coming back to this picture here. I'm going to calculate that guy. And then I'm going to do one that they don't have on here. It's basically this, but kind of, if you were to think of this picture as being just as thin as that, so that the length is shrunk down, you kind of think of it more as a disc, right? In fact, if we made it infinitesimally thin, then it becomes a two-dimensional kind of figure, right? Because it's just like a little flat disc spinning with an axis going to the center if this L is really short. So I'll go to that, to the disc, and then I can go from the disc to this guy, where it's actually much longer, and show you that I can derive all three of these. Well, they don't have the disc here, so that moment isn't there, but this guy, and then, well, it is kind of there because, well, we'll see. I'll show what it is. You'll show that it ended up being the same as this because the L doesn't matter. But it's probably why they don't have it on there. But anyway, it's nice to kind of see that from scratch. And then you can do the others, so you have the answers here. So you can go through and see if you can kind of construct, see how if you can figure out how to get all those from get these results that they have. You're using the methodology that I'm about to show you. And again, those are all double and triple integrals and things. There was no one-dimensional figure there, but you get around that by doing the integral by using mass density to convert to an integral over a single variable and choosing your differential masses wisely, which, as I say, I'm about to illustrate to you how to do that. But any questions? Because that's really basically it's all going to be mathematics. It's just integration and showing how to set up the integral. There's not going to be anything else that we will talk about, any new implications or properties that we're going to get out of that about the concept itself, the concept being moment of inertia. One thing I will say before I do this, though, can anyone, now that you understand moment of inertia, before we do the integral stuff, can anyone give me some examples of where understanding moment of inertia has seeped into popular culture quite significantly so that we see it kind of all the time, even though you might not have known why, certain devices and instruments and things that you've been buying have been made that way, but it's pretty obvious a couple of examples. Anybody want to take a shot? You know what I'm talking about, or can you just think about it?
Probably like a record player, like the disc.
What about the disc?
How it needs to be long in order for it to be well balanced, or no?
Well, I mean, as long as it's even, it's going to be balanced. As long as it's it's uniform density and it's kind of made symmetrically. It's not going to affect the balance necessarily. I do think that the larger discs, the albums, have a larger moment of inertia than the smaller discs, and that's actually an interesting point. It's actually an interesting point that you make because I never thought about this. There is a relationship, I would say. I don't know if because I grew up with turntables and hi-fis. I don't know if most of you, if unless you have one, because they're starting to kind of remake them now. But for a period of years from the late '80s until probably 5, 6 years ago, they stopped making hi-fis because obviously it's obsolete because we've got digital. It's always going to be better. Well, not necessarily better in some ways in terms of saving the data and stuff like that and transferring it and buying and selling. But in terms of sound quality, I don't know. Some people say analog can be just as good, but it depends on the digital stuff. And now it's going to be better because even the cheap digital stuff is really. But initially, you had to spend a lot of money to get the good digital sound equipment. But now, your cell phone can do everything, right? So, anyway, my point, I digress. But my point is that if you notice on those turntables, on a 45, the speed was, I forgot what the number of revolutions per second. I don't know if it was it RPM or was it, yeah, it was RPM. I think it was recorded in RPM, and it was revolutions per minute, I believe. So like a big 45 would have to go around, I think it was 33 was one of the setting that we would use for the larger album, the 12-inch. And the 7-inch, which was called a 45, I don't know. I'm just trying to think why they call it 45 now. But it had its speed it might have been 45 revolutions, but maybe that's why they called it a 45. I can't remember. Just thinking of the numbers on my old Wi-Fi. But one thing that I didn't think about at the time is I always thought it was a faster speed, but I don't think it was a faster speed. It's a faster period, a higher frequency or period. But we'll show, I've already shown you, like the relationship between speed, the actual speed of, you know, the portion of the particle that's going around is equal to r, the radius that it is from the axis of rotation, times the angular velocity. And the angular velocity is just basically frequency. Angular frequency, angular velocity, same thing. So I think that you might have had to have a I don't know, maybe it was slightly different. A different period in order to have a very similar speed of the linear speed for the disc rotating under the needle. I don't know. Or it might just be because it's more massive, you need more power to get the same amount of rotation. I don't know how it was calibrated. But that's not directly what I was talking about. That's not directly associated with moment of inertia. A more practical example and useful, where you would feel it if you were using it, are the design of the wheels of bicycles now. It started with like the racers, the Tour de France, where if you look at those, even though the tires are very thin, the rims are made of kind of a pretty heavy alloy so that the wheels are heavy. They can be thin and still heavy at the same time. They're thin for obvious reasons. And even now, in some of the more, like Tour de France bikes, they put I think shields on the spokes so that the spoke they cover the spoke so that the air can't get between. And it gives kind of a design like there's a cone fitting over the portion, a very thin cone. And that, that's light material. That probably doesn't have a lot of weight. But what I'm talking about is literally the rim, the thing that the inner tube is sitting on. That thing is heavy. And it's because what they want to do is increase the moment of inertia of the tires. Now you might think that of the wheels. You might think that it's counterintuitive because you might think, well, if I'm trying to go fast for long distances, why would I want the wheels to resist rotation, turning around, right? And that's because, again, remember the subtlety associated with the moment of inertia. I said it earlier on in the properties. Moment of inertia is not resistant to velocity. It's not resistance to motion. It's resistance to change in motion. It's hugely significant, and it makes a big difference in this, in those subtle in this example. If you have to race 26 miles, over a period of days, most of the time you're not going to be accelerating and decelerating, at least not more. There's an average velocity that you're going to be closer to during the long stretches that you're riding. Now, yeah, if you're going uphill and downhill, that balances out. But I'm guessing most of the length is like long distances. So you had to accelerate, took you a couple seconds to get up to an acceleration. And then you're at a specific velocity that you're going to maintain, kind of like a long distance runner. Well, the moment of inertia hurts you when you're trying to accelerate, going from 0 to 25 or 30, whatever your average velocity is. But once you're at that average velocity, you just want to maintain that for 8, 10 miles. Well, if the moment of inertia is higher, and moment of inertia is defined as resistance to change in rotational motion, then it's going to be harder for the wheels to slow down because their moment of inertia wants to keep them moving at whatever your average velocity is. So that means that you would have less effort, you put in less energy to keep those tires at a larger velocity than tires or wheels that would have a lower moment of inertia. And it makes a difference, a huge difference, because over time, 3 days and how many ever miles, that amount of difference in energy and effort to keep the wheels at that higher average velocity would be more if the wheels had a smaller moment of inertia. And you see that, so that first started with the designs of those racer bikes, but you actually now see it spilling over into all these little renting motor things you can buy, all of them, especially the bikes. See how the bikes, they're really rugged, but they also have the tires with the big rugged wheels on them on the end. And these things are electrically powered. So basically, it makes the bike more efficient to have those bigger wheels on there. It's really counterintuitive. You would think that it would use more gas. But even like cars with when you get the big wheels, when you get cars that have the, I don't know, 20-inch, 19, whatever, the bigger and the thicker the wheels, the more gas you save over time. And with electric cars, it looks better, it's nicer, right? You know, a lot more expensive. But it's not just that it grips better, it actually makes your car more efficient to have bigger wheels, you know, big rims and bigger wheels on the car, whether it's electric or gas, than to have the smaller wheels for that reason.
So that's actually pretty cool because like you say that because when I was buying my first car, uh my mom was emphasizing like, oh no, don't get uh the car with with those kind of rims, get the stock rims because it's gonna save you gas. And just to hear you say that it has to do with the moment of inertia, that's very interesting.
Yeah, it's very interesting. And there you go. I mean, this is why we study science, because there are these things that, you know, and you see in popular culture and politics, you know, it all goes crazy. People they have all these other agendas, even if they don't realize it. But one of the reasons science can be really tricky is because there's some things that are they're really counterintuitive, and you would never know unless you could figure it out from the base concept and basically figure out the concept that defines it. And so it's really, you know, it really shows that it's important. You know, knowledge is important to have a really good understanding. And you know, there are nuances to it, right? Because if you had the car on a day where you're driving around in the city all the time, it might not appear that you know, it will be less efficient. But you know, everybody knows that, you know, inner city driving is less efficient than on the highway. But where it really would make a difference, and you would notice a huge change, is that if you were traveling long distances and you were comparing smaller rims to larger rims, it would probably be a quite significant difference. Like if you're going halfway across the country or something like that, you could see the big difference in the amount of gas that you spend. It'd be harder to determine that difference in the city. But yeah, that is a wonderful. I love to point that out for that reason. But there are other things. You know, that's just one little example that pops up because there's not that many examples that pop up in mechanics at this level where you can really show why knowledge is so important, and why understanding the physical analysis of a system is important. But when you start to get to other things, you know, on terms of astronomy and even electricity and magnetism, where you know you run across these examples where you get something that's hugely counterintuitive, and you realize how difference it makes and what a difference it would make in terms of your understanding and designing a device to exploit that difference or not. We'll talk about some of those things later, like you know, like you know, resistance, for example, and why something like a bullet train in China is so cost effective, and why Elon Musk wants to build basically the same thing, and why it makes sense to do something like build a train from LA to San Francisco. Yeah, yeah. All right. Well, ooh. Oh yeah. So I got to do the integral stuff. So got about 10 minutes. I can do one or two in 10 minutes. Oh man. What was that? Oh, I was knocked down here. Just knocked over my coffee. T. That's all right. I've been cleaning my carpets recently anyway. That's why I don't have my bookshelf up here. So I have my carpet cleaner out. Knock that out real quick. Yeah. Yeah. So we're gonna do the ring first. Okay. So I've got a that's a disc. Yeah, here's a ring. Yeah. So we got a ring, and it's just literally a ring. Like if I were to take a string or something and make it like some sort of rigid string, or I connect it into a disc like this, and it's circular and it's rigid, and I just spin it around, right? Either horizontally or whatever. So that's what we're talking about. What would be the moment of inertia of that thing? So I can have a couple different views of the ring. So a ring. And we can say the total mass of the ring is m. Or a lot of times people, do it in terms of mass density. I think I talked to you before, but let's just go ahead and run out of time here. So I'll give a three-dimensional axis first, and then we'll give a two-dimensional top-down view axis. Okay, so let's make the z-axis straight up. So I'm changing that a little bit because in your book that's what they do. I've been doing y up and x to the right, but if z is up because of the right-hand rule, x has got to come out, and then y is over here. So you have x, y, z. Now let's place the ring in the xy plane. So it's a ring that's lying in the plane and just kind of looking something like that. So in fact, if that's the case, this should probably should be behind there. So it should be like that. And its radius, a or something. If I'm looking straight down on the z-axis, it's literally just a ring like this. And I guess if I'm looking straight down, then I flip the y would be to the right, positive y, and positive x would be straight down. And so this is the z-axis here coming out of the board. And so let's have the rotation be looking down the z-axis, let it be counterclockwise. So the rotation is around like that, and here it would be like that. All right, so that would be omega. Right. And omega, yeah. So what's the moment of inertia? Now, the way this works is we have to get a differential element. So it's kind of like we take the thing and break it up into differential elements of differential mass dm. So that's like a dm. And you break up all the different ones going all the way around, and you're kind of treating those like particles. And so you just add them up. You find the differential mass, the moment of inertia associated with just that portion, and then you add it up as an integral to get the differential, to get the moment of inertia of the whole thing. So and again, the perpendicular distance in this case would just look like a position radius vector, but it's really perpendicular distance, so don't forget that. And yeah, we'll just I'm going to call it r. It's just that distance. The question? Now, okay. Yeah. So I'm going to start off with the integral form. The integral form is I equals, r squared dm. So with integration, one thing that we do is just the same thing we did with the guy before with moment of center of mass, is that I'm going to be employing mass density. So in this case, I can employ a linear mass density, a lambda, and I am going to convert from an integral over mass to an integral over coordinates. So my differential mass, I'm just start renumbering here. I'm saying this is a thin line, so it's distributed over a linear geometry. So I'm going to use linear mass density and say that lambda, the linear mass density, and there's a couple ways you can write it. It's either equal to the total mass over the total length, and the length here would be the circumference, right? 2 pi r. Or it's a differential mass over a differential length, but that differential length is kind of like an arc length. So I'm going to just call it ds. ds. And sometimes people have a coordinate. They can write it as a coordinate, and that would either be the coordinate m and the variable coordinate s, meaning the linear length around. But that's not going to be applicable in this particular problem. But I still like to write it because that is true, the mathematical truth. So what I'm going to use for my integral is, so these are really 3 or 4 different equations. So what I'm going to use is this guy, lambda equals dm over ds, so that I can substitute in for ds and get dm in terms of the integral over the length, ds. Effectively, it kind of converts it to cylindrical coordinates in a way, but I'm not going to kind of present it as that because it doesn't have to be. That sounds all complex. It's not really. It's actually just more intuitive. So using the particular version, lambda times ds equals dm, I'm going to substitute equation 3 into equation 1, and that converts this to I equals the integral r squared lambda ds. Okay, so ds, and yeah, sometimes when I'm going through the problems, I write it here that dm would be equal to lambda ds. Once you understand that, then you'll kind of know it immediately. And I just like to write it out, in my problem solving technique. I would probably put it up here, lambda ds. Clearly showing that I've transitioned from an integral over mass to an integral over coordinate s. Now, s is really an arc length. That's not really my x, y, and z coordinates. And so if I look at my picture here, as I move along, my r is not changing, but my arc length is changing, right? It's changing, and how it's related to, as my r changes, the position r of this differential mass, say right here, is going to be at a different angle, right? So that's still r, but I have a delta theta in here as it goes around. So that implies the arc length formula. And so I'm going to go from length basically to integrating over theta. So that I'm saying that if s is equal to r times theta, then for a constant r, you could also say that ds is equal to r d theta as the angle changes. So one more substitution, putting that up into that guy, and so I get 6, 7. Moment of inertia is equal to r squared lambda r d theta, and the r is going to go from and r is constant, so that's cool. So I don't have to integrate it. So that r times that r is r cubed, and so the constants of the integration are going to be so I get r cubed outside, lambda outside. So this just goes from it's just d theta, which goes from 0 to, it goes all the way around, so 0 to 2 pi. So I'm going to end up with the moment of inertia in terms of mass density is equal to 2 pi r cubed times lambda. Now that may not look reasonable because that's not what we had in the book, but that's because they had it in terms of mass density. Generally, you present moment of inertia in terms of total mass, not mass density, although this is absolutely correct Basically, the problem is done at this point. But then I can go back and grab this guy here, this version of lambda, with the total mass, that lambda is equal to the total mass over the total over the circumference, but the circumference is 2 pi times r. Right? So when I substitute equation 10 into here, then you'll get the equation that they have there at in the end of the book, that we were just looking at in that chapter. Just looking to see if I had come back to the class view as opposed to the screen view. So putting equation 10 into this guy, you're going to get that I equals, what was it? Yeah, something. 2 pi times r cubed times quantity m over 2 pi r. So 2 pi r cancels with 2 pi and one of the r's, and there we have what they have. That the moment of inertia for a thin ring rotating about an axis through the center is equal to m r squared. And that's their answer. Now it looks like we've run out of time. What I would do is now go ahead and do the thin, do a disk. So like, do the same problem, but now the mass is distributed over all the whole portion, over all of this. And one of the ways that you can do that integral is you can just your differential element now can be a ring, so that you have rings of different radii. So like, like if I draw it out here, you'd have a ring like that, then a ring like this, then a ring like this, going from all the way out. But then you would have to convert from your dm. In that case, the mass is distributed over a specific area. So like it'll be a ring of radius or circumference 2 pi r, but then you have a small dr on there because it has a little width. And so and so the dr then would go, you'd then you'd be integrating the r. In other words, you have to think about it, but I'm see if you can figure it out. But the sigma would be equal to the total mass over the total area. Is that true, or is it just I've done it here? So what did I do? Total area. So you have to kind of make up something. The area is actually going to be the circumference. It's kind of a made up quantity, 2 pi r. So that's just the circumference. But then if you give that ring a little bit of a lip, it kind of like a thickness, then it's like the thing is, the r is the distance that it is away from the center. So use red, I guess that's what I was using for radius. So that distance, it goes out to r, but then it's got a little bit of a thickness on it. So that thickness, in the direction along the plane, so that thickness there is a dr. So the way you get area is you just have, the 2 pi r times the thickness dr is going to give me units of meters squared. So the mass density, then the equivalent of this equation would be total mass over total area, or differential mass over total area would be, that's a good one. That's actually, so differential mass is 2 pi over r dr. So that's actually for the differential. for the total area, total circumference is 2 pi r, and then thickness, yeah, I guess it would be no, sorry, it's just the area of a disk, which is pi r squared. Yeah, so that would come out, it would be r times r, but there would be no 2 in there because of the integral on the r. Yeah, the total area would just be pi times the total radius squared. So this is a variable. I guess I didn't define that. Yeah, the total radius would be r. So that would be, so this term would be equivalent to this term, and then this term would be equivalent to this term. And then you would just have the variables there if you wanted them. But you really just need these two terms. And this is the one that you would use, kind of. And so if you try to, do that integral and mimic what I did, you should come up with the 1/2 term that they have there. Yeah, and then the problem that they do have in the book is that they kind of give this a length, right? So they say, okay, well, we're going to give this a length. It's going to come down like this, right? So there's an L here. And it turns out that that problem is the same as that problem because this L never comes into play. So if you figure out how to do this, this problem, then that problem would be exactly the same way. But it's worth it to go through and kind of see it for yourself, and you'll come out with the same answer, which I believe for both of those is 1/2 mr squared. So it's just, sometimes you just have to spend time with the stuff yourself and work through it. It's one thing to hear me say it and even see that this is somewhat simple. But it's, there's some subtleties in there and that you just can't know what those are unless you work through it yourself. So I would suggest that you do that. And these are like the simplest ones, and then you can start to maybe go on to some of the other symmetries, like the spherical symmetry and then the different boxes or rectangular type shapes, what they do there. But I would start with that. And that's moment of inertia.